Okay, so hello everyone. In this video, we'll be discussing the pumping lemma, which is a lemma that actually allows us to prove that a language is not regular. So this is a pumping lemma. I'm going to first avoid reading it word for word, and instead give you some intuition as to what exactly it's saying. So what the pumping lemma is saying is it's giving you a sort of way of characterizing this property of regular languages that we talked about before, in the sense that um, regular languages are sort of bijective with this notion of a finite number of memory, or reducing the patterns of the language to a finite number of, say, cases. Okay. So the intuition that I think at least that I've made myself believe for the pumping lemma is that it kind of characterizes what regular languages are supposed to look like. So the pumping lemma gives you the characteristics of a regular language. So in other words, it's saying if this language L is regular, then some properties hold. Okay, and these properties that must hold really have a direct relation with the DFA that recognizes the language. Okay, and so in a DFA that recognizes the language L, and here I'll have to note though that L, we're going to specify, is an infinite language. Okay, so otherwise this intuition kind of breaks down, because this reduction of cases, if there's a finite number of cases, right, because there's a finite number of strings, then this reoccurrence of patterns won't really work, and so then you might not get um, the satisfaction. That's not a word. The You won't get satisfying the pumping lemma conditions, essentially, or not necessarily. So if you have a DFA, right? So you have a DFA M that recognizes L, okay? And L is infinite, but M has a finite number of states. So, first of all, that's kind of interesting, right? You have an infinite language, right? So you have an infinite number of strings. L contains an infinite number of elements, right? But the thing that recognizes it is finite, right? The thing that recognizes it is an FA. It's a finite automata. Well, that's quite interesting, right? Because you have an infinite amount of information, and it seems like you're boiling it down into a finite number of states and a finite number of information. So how can you actually do that, right? Well, you can do this, right? Because somewhere in your FA, right? Somewhere in your FA, there's definitely going to be a loop, right? So at some point in your machine, right? At some point in your machine, you're going to have a state, right? Some state where it can branch out of this state, right? You'll have a branching out of this state, and you'll have a path that goes from the state back to the state again. Okay, so this must occur because the intuition of why this must occur, at least, is that you're trying to fit an infinite number of strings into a finite machine, right? And so at some place, there's going to have to be a spot where you're going to have to loop through an infinite number of strings, right? So you need some kind of loop, right? You need some kind of loop. You need some kind of loop to iterate through an infinite number of things, an infinite number of strings, right? So otherwise, right, if there's never some kind of recurring state where if you go out of that state, at some point you can go back, right? Then that means that all of your machine is laid out flat, right? You can think of it as writing down all of your states, making them all explicit. So all of your states have to have one explicit role, and they can't have transitions returning back to them. But then what's going to happen if you have a machine like that is that it's going to keep branching out, right? So if you can never allow something like this, if you can never allow a recurring state, let's say, then you have to keep branching out, right? You have to keep branching out, right? So you have to keep doing this. You can never go back to one of the states. And so if you keep branching out, which you have to do because you have an infinite number of strings, right? Well, then you're going to create an infinite machine because this branching will never stop, right? And so what the condition of the pumping lemma says is that, well, actually, if you want to stop this branching and you want to, if you want to stop this branching and make your machine finite, then at some point you're going to have to end this procedure of branching out, okay? And you're going to have to say, well, if I'm at this state, now actually, if I read something, I have to go back. I have to essentially recycle or reuse states, okay? So that's really the crux of what the pumping lemma is saying, right? The condition in the pumping lemma is that it's saying that if you have this FA, this finite automaton with a finite number of strings that needs to process an infinite number of strings, that needs to recognize an infinite number of strings, then it has to reuse states, right? Transitions have to go back to some of the states. Otherwise, you're going to keep branching out, right? If you keep branching out, you get bigger and bigger and bigger, then you're not going to have an FA, right? You're going to have something that's infinite. Okay? So that's what it's saying. And then what the pumping lemma specifically targets is it targets a state where you have this recurring pattern, right? So it says that because L is regular, then you have to have this kind of reuse or recycling of a state. And so then if this, right, if this is the string Y, right, because to go from this state through these transitions, through these states and transitions, and to go back to the state, you need to read a string Y, right? And so if this was what was before the state, so if this was X, and if this was what what was after the state, so if this was Z, right, and Y was the thing that was reoccurring, right, then what the pumping lemma says is that if X, Y, Z is an L, right, then it doesn't matter if you repeat Y once or 3 times or 17 times or no times. All of the other repetitions, right? So all of the other repetitions, if you repeat this I times, right, this should remain in L, okay? That's what the pumping lemma is telling you. It's first basing its idea off the fact that a state has to be reused, and then saying, well, now take the stuff that goes through the state that's being reused. If you pump through that state, hence the name pumping lemma, if you pump through that state with the string Y a bunch of times, right, or no times, and you just go through it, right, if you pump down, meaning that you ignore, right, you ignore this loop and you pump down, then in any of the possibilities where you pump down or you pump up, which means that you go through this loop more than once, you're going to have to accept this string, right? So this string is going to have to be accepted, or in other words, it's going to have to be an L, okay? And so this is what the pumping lemma tells you. And so formally, now we can actually read it a bit more formally, and it's not going to seem too crazy. So we have L, which is an infinite regular language. Okay, I've told you why it has to be infinite, because if it's not infinite, right, if you have a finite language, then conceivably there might be a language where you don't have to repeat stuff, right? Because maybe you can do something like, oh, I don't know, like something like this, and then this, and then this, and um, this goes to a rejection state. Oops, why can't I write over there? Oh, I see. So you go here, you reject, and here you also reject, right? And here you accept, and then here you reject. Okay, so here to get to an accept state, right, there isn't a loop here. But this is because what you're accepting, right, you're actually just accepting two strings. You're accepting AA, and you're accepting, it looks like BB, right? So this only works really for an infinite regular language. Okay, so you have an infinite regular language, and then the pumping lemma says that there exists some positive integer m. So essentially, there's by the pigeonhole principle, that's essentially what we're going to be using. There's a threshold, right? There's a number, there's a length m, right? For which if you go past this length m, right, and you go through your machine, you're going to have to start repeating, right? You're going to have to go through this repetition, right? So there's some positive integer m, right? And so typically this is usually justified by the pigeonhole principle, okay? Such that any string in L has a length at least m, right? So it's past this threshold m, can be decomposed into three parts, right? So this is the first part. This is the first part of the string where you reach the recurring state. Then Y is the part that loops, right? And then Z is the remaining part. Okay? And so what it says is that actually there's a few more restrictions. It says that the length of X and Y has to be at most M, right? Um, which makes sense, right? So the recurring pattern has to occur in at most m transitions, right? That's why m is the threshold, right? Otherwise, the threshold would be larger, right? So xy has to be within uh, length m, and y has to be length at least one. That just means that you have to have at least one loop, right? So the smallest possible loop you can have, right, is a self loop, right? So this would be if the length of y is equal to 1. But you could also have the length of y is equal to 2, right? And so on, right? So there's a direct mapping between the ideas or the definition, sorry, the notation in the pumping lemma and their sort of equivalent idea in the DFA. Okay, so you have this loop which has to have length at least one. Okay, and it says that given these conditions, right, no matter how many times you go through this loop, so if you have the string yi, which is equal to x, yiz, which just means looping through y I number of times, okay? If you loop through y I number of times, then x, y, z is also in L. And so here this just tells you, like I said, you can either pump down, right? So pumping down usually refers to I equals 0 is pumping down, it means that, so it means that W0 is XZ. So you essentially just cut out. You think of it as chopping off, right? This self loop or this cycle, right? Or you can pump up, which just means going through the string more than once, right? So then I greater or equal to 2 is pumping up. Okay, this is exactly what the pumping lemma is telling us. Okay, and so the other way that I like to think of the pumping lemma is just a sequence of 4 statements. Okay, so what are these 4 statements? They start with if L is an infinite regular language, then what? Then, first of all, there exists some integer m, which is positive. Okay, so there exists some integer m, which is actually sometimes referred to as the pumping length, or sometimes the integer in the pumping lemma. Integer in the pumping lemma, right? So we're saying that there exists some positive integer m, okay, such that 2 for every string in L with length greater or equal to m, right? So this is the second statement. It's a for every. So you have a there exists, then a for all, right? For every string with length greater or equal to m, you can decompose it, can decompose 3. So there exists a decomposition of W, which looks like X, Y, Z, with the length of XY at most M and the length of Y at least 1. Okay. And then, so this is the third statement. And the last statement says, such that, right, so there exists a decomposition such that for every I greater or equal to 0, Wi x, y, I, z is an L, right? So either you pump up or you pump down, that's going to be an L, right? So what you'll notice is that this is a sequence of there exists for all, there exists for all, right? So it's saying there exists some threshold where any string past that threshold can be decomposed such that when you pump up or down, you belong to L, right? That's what the pumping lemma is telling you, no more, no less. And so we're going to see that we can actually use the pumping lemma, quite incredibly actually, to prove that a language is not regular. So here we see that this is if L is regular, then some property. We'll see that we can actually inverse this statement to show that a language is not regular.